Hello everyone. Today we talk about CPU architecture and instruction decoder and cache and memory. Mainly the architecture is today's topic. Now, when you talk about CPU architecture in the textbook, usually it shows like register here, memory interface, instruction decoder, and execution unit like ALU, something like that. But this is the hardware diagram, it's not the architecture. CPU architecture is it's architecture. What determine the CPU architectures? CPU architecture determine the technology, hardware you use, what kind of, say, number of gates you can put on one chip, and number of pin, what kind of package you can use. It's all affect the CPU architecture, and also algorithm. And others like requirement on chip, analog circuit, AD converter stuff, and program itself can be on chip, so microcontroller. So these affect architecture. So depend on the needs, you have to decide what kind of architectures you're going to make. And making architectures like analog designs require quite experience. You have to know all the pro and cons of the architecture. But in order to do that, first of all, let's understand what the CPU is. CPU is actually state machine, and make it programmable. And so you know the story, the Intel made the first CPU chip 8080, but this is not the beginning of CPU actually. It's the CPU existed, computer existed. The IBM had a CPU. It's a multi-board CPU. So I would say what's new in Intel's the CPU is a single chip. CPU. Well, single chip include all the memories and everything you need? No. So the 8080 made a lot of hardware consideration and come up with this much we put in on chip. Okay, typical hardware element on chip. So memory will be outside, and the CPU and some I/O port, control or sense, anything here, and the memory is for programming. So this partition of CPU, the architecture, is the first single chip. But now it's many different kind of CPU chip. So architecture varies greatly from microcontroller to AI CPU, the web server CPU. The architecture is completely different. Okay, that's the progress of hardware, number of gates, increase significantly, and number of pin also increase. In the beginning, we use this type of IC chip package. Now we use this square one with pins on the back, and 256 pins is common. Okay, so this time we had about 20 pins. So hardware, what we can do to make it, the hardware technology changing, and the algorithm had a great advancement. The algorithm was somewhat limited because of the hardware cost, but now hardware is cheap, so all kind of the mathematical development to do that work, the algorithm has been improved significantly, and all type of the CPU architectures. Okay, so what is a state machine? Programmable. When you talk about state machine in the textbook, usually a traffic signal. Say you have a green, and when timer expired, then it become yellow or amber, and timer expired, become red, and timer expired, then come back to green. This timer is for the automatic traffic signal, but this timer, when you push the button, one of those signal, when you push the button, it's all usually red here, usually red. It stay red until something happen, command is given, and this command is it doesn't go this way. Usually this stay here. Only if you push the button, then signal start changing for pedestrians to start walking. So this condition become push the button, right? Then it goes through the cycle again, and come back and stay there in red. So the timer expired, go back to beginning, and just keep repeating until somebody push the button. Okay. Now, who pushed the button? Human push the button. So we put the little circuit here, the ROM table, and has a timer value depend on the day. It's 1 o'clock, 2 o'clock, so and so. And busy time, there are so many people walking on the street. The busy time, timer become very short. So that means depend on time, push button automatically by this table. So what's happened? Suddenly this is programmable state machine, because like a morning time, busy time 7 to 9, this automatically traffic signal goes through cycle more often. And non-busy time, like night time, it doesn't even push the button until human actually push the button, right? So it's traffic. This become programmable state machine. So this is actually CPU. And the task it does, it's not the arithmetic unit, the calculation of the value and so on, but it does certain task by state machine, and state machine is programmable. Okay, so this is very small CPU. We can call that CPU. It's actually state machine. What's the difference between state machine and the CPU? It's like what the living cell and the virus, right? The virus, this is sideline talk. Virus is molecule, but act like a living. So this act like a CPU, but look like a just state machine, hardware state machine. Okay. So from this perspective, we talk about CPU architecture. CPU architecture, what we need is instruction decoder. Instruction decoder has instruction register and the address, and the address shows where this instruction come from, like memory address, to E F A, whatever. Okay, and here's the instruction. So there is a memory interface to go to the memory. Memory has program, and when instruction is empty, then go fetch the instruction. Okay, when new instruction arrive, what's happened in CPU? This instruction is decoded. Here's a difference between CISC and the RISC. Okay, the CISC architecture was adopted by IBM in the beginning to reduce a lot of random logic. This instruction in the CISC point micro controller, or whatever you call micro instruction unit. This is actually ROM within the CPU, and there's a counter, and counter execute one by one. What is this output? It's like, okay, it's a control, register read and register write, and ALU left side input, ALU right side input, and the ALU function control. So this ROM actually go there and controlled execution unit. What is execution unit? It's like temporary data holder, which is register, and execution unit. This is the execution unit. Okay, CPU does some work, all controlled by this internal microcontroller ROM, and the ROM just sequence the signal for controlling those. This is CISC, right? But the RISC, this goes to instruction decoder, and it's generate various signal, and this signal depend on the CPU and set of instruction. If you reduce the instruction set, this can be manageable. If instruction like a CISC can handle even divide, sign, and those calculation, it takes like over 100 clock cycles. The RISC eliminate those, so this control can be managed without this microcontroller ROM inside the CPU. It's just random logic. instruction, we call that instruction decoder, and decoder controlled execution unit, right? And when it's done, send a signal to this instruction decoder to get the next instruction. The next instruction, its flag become empty. Here the instruction become empty. Then request memory. This is the state machine, so it's goes step by step like a traffic signal, right? Is now request and wait for the memory to send the data, next instruction come back. And if it's a jump instruction, you calculate using ALU, you calculate and change the address here if jump instruction, right? And request fetch the next instruction. In next instruction, the fetch request come, memory interface, go get the program instruction, come back to this instruction register, and that is decoded, and do the execute. Okay, now this execution time, how many clock it takes, that's called latency. Okay, and like a multiply is a big operation, goes through a lot of logic to get the multiplication finished. So it has multiple latency. How many clock? Usually number of clock is the latency. Okay, so the latency is going to be controlled by this one of the signal from decoder. Say if multiply and if takes 4 clock, then initially it's send out the first clock task, and this change to L2 signal, L3 signal, L4 signal, just like a state machine, right? Then go back and request next instruction. Okay, now what makes CPU complicated is cache. Because the memory interface takes a long time, like a 20 clock cycle to access the memory. Depend on CPU. When CPU gets faster and faster, and the memory stay relatively same speed, then it takes like 20 clock cycles for CPU waiting the next memory content from memory unit is like it taking forever, right? So in order to improve that part, no matter how fast CPU is, memory slow, then CPU performance drop. So when you request memory, when you have a cache, you check cache, see if cache has instruction looking for, and when it's search address. Do you have instruction from this address? And there is one here in the cache. Then get it done here very quickly. Okay, so the cache is to speed up the memory interface, but cache size is limited. It's a hardware limitation. So how much program you can put in the cache? 10% or 20%? Very small, right? And cache has both sides. You have to consider read and write. If read, the cache, if you search for the address you need and it's not there, then memory the interface go back to program and get the instruction and put the copy into the cache, right? Then if cache is full, there is a certain algorithm for the cache, round robins, all kind of the algorithm used, first in, first out. For example, the simple case is the cache remember the beginning and ending, and last one is the latest one. So first one is like old data. It's overwritten by this newcomer when memory fetch the new instruction from the new address, and that's replace it. And that's the way cache keep the latest used instruction. And this makes sense because when program has a loop, you repeat and go back, repeat the same thing many times, 1,000 times. The most likely those instruction is in the cache, so you don't have to go to the memory to fetch it again. It's all in the cache. Okay, so that's for the read. And sometimes read cache and the write cache is mixed together, but sometimes it's separated, depending on the characteristic of your CPU application. When you write data, writing takes 20 clock cycle or so. If you send it to memory, it's very slow, right? So what you do is you write this into the cache, and you may use it right away. For example, like load save, the name of instructions depend on the CPU. Like save data A to address, right? And next time you use few instruction later, load A from this address. Okay, so you save it in memory and bring it back again, and it's just wasting time. So you put this data into the cache, the right section of the cache, right? Then you can use it again. The problem is this data is not in the memory. Okay, so multi-CPU system has a basic problem here. If you have a memory and this guy has a cache, he said, okay, I wrote it into this memory address, but it's not written. This CPU 2, go there and think data is get the old data. The actually new data is in this guy's cache. Okay, so cache coherency problem has to be dealt with. Now, one way to solve is when you write it, but immediately write it back to memory. It's called write through cache. Okay, write through means whenever you update the cache, it's also update the memory so that other guy can come and get the most updated data. So that's the write through, one way to do it. But this is going to have a performance implication because every write you bring it to the memory. You know, this data you may modify within a cache. Why don't you just modify first before you bring it to memory, which is costly in terms of number of clock cycle it's consumed. So but you don't know in the program, general programming is when you're going to modify that data in the cache. So what you do is this, and also when you use a cache, you write the data, eventually this cache become full. So what you do, so there is an independent state machine for the write cache, monitoring a situation. When cache become full, then you have to get rid of something, and in order to write this into the memory, you cannot reuse this cache in order to write the new data from the CPU. So what's happened is there are many different algorithms people use for the CPU design. When the write cache usually has contain two kind of data. The one is a dirty. What is dirty data? Is the new data written by CPU, and it's not written in the memory. And the clean is, hey, this guy I wrote it in memory, so you can use this space for rewriting other data. Okay, this ratio is maintained into certain ratio, and whenever the dirty section increase, then this state machine start initiating to write back. Write back means write into this memory. This is called the write back cache. Okay, so I told you cache is the complicated part of the CPU design. We have to do this because we can't have the entire memory on single chip yet. I mean, we're getting close, but still not, because memory size keep increasing, and there's no way you can put entire memory chip onto the CPU chip. If you could do that, then the access time to memory become much less, like, okay, maybe 3-4 o'clock. Then you can get rid of the cache, right? And we don't have to design such a complicated CPU chip with a cache. But this, whenever you make a CPU architect complicated, then you have a following problem. How do you test it? And when you do testing by simulation, all kind of cases you have to test it out, and you probably cannot cover every single cases that may happen in a real CPU operation. Then what's happened is CPU may work for 1 month and cause error after 1 month, kind of things. So it's become much harder to design entire system. But anyway, the write back, some independent write back state machine monitor the situation and manage it. And the idea is, well, if you have a bunch of write from CPU, it's fill up, but it's not keep writing. CPU do something else. CPU become busy for something else. While CPU is looking the other side, this start writing memory to make a dirty cache clean. Okay, and so you go average. You go by average. How many data CPU write into the cache, and that determines this ratio of dirty cache and the clean cache, and that's depend on the application. If CPU is general purpose, that run the Linux, so there will be some disk management operation OS use, and the application program use here and this memory address. So it's going to be the usage of memory. The memory address is concentrated on OS busy area and application, 1 busy area and application, 2 busy area, so and so. Okay, so this kind of characteristic is going to affect the architecture of the CPU cache algorithm. So depend on what kind of CPU. If you're using the not the Linux but general purpose control system, the OS is not like a Linux, but it's like a TOS, the machine control OS. Its characteristic is totally different. You don't have disk management area stuff, so it's all depend on what the purpose of this CPU is. You can't just design one CPU that's fit to every application, and that's why the CPU design is required for every application, and the users hope that some general purpose CPU fit into his application, and if it satisfies 80%, you're lucky, use that CPU for his application. Okay, but it doesn't satisfy when it's come to like a web server. General purpose CPU architecture is not good for web server. Well, it doesn't satisfy for the AI calculation. So it's become it's become a different architecture CPU chip. Okay, so I hope you get the overall picture of the CPU. What we do is, from next video we will take each the hardware piece within a CPU and show you how the real chip is designed. Okay, so please subscribe so that you get the next video.